Getting back to 11.3. So, another thing that we can use dot products for is this idea called a projection. Yeah. One application of such things is that we can actually take vectors, kind of like the one shown here, and break it down into what we call orthogonal components, right? So when I say component, I'm not talking about like the x component, y component, z component. I'm talking about a vector component, which is different. Um, the way that it's different is essentially any vector can be broken down into two different components that are orthogonal, or remember, perpendicular to each other. The example here is we have a box or an object or something that's being pushed up a ramp by this person. The box, if you were to let go, would come sliding down the ramp on its own. Run away. Yep. And the reason for that is because of this force due to gravity, right? The fact that gravity and the weight of that box are kind of going in this direction. And the way that we stop that from happening is we apply enough force to the object so that the force applied is at least, so exactly equal to or more than um, the amount of force that's being applied by gravity. And one way that we can actually figure out what force it would take for our buddy here to not get run over by that um, is to decompose this gravity vector, this gravity force, into these two components, right? Whatever the magnitude of this is, that is the force that needs to be applied to keep the box from moving down the ramp. Right? If we exceed that force, then we'll be moving the box up the ramp. And there are a lot of things that kind of come into play there, right? Gravity is only one of the forces being applied. Right, but for the sake of understanding this concept, let's only look at this one vector. All right, so the vector pointing down, we're going to call G for gravity. Okay, the vector along the ramp is R1, and the vector that's orthogonal to R1, we're going to call R2. Okay, now this next little paragraph here is important to know because when you talk about projections, it's really important to get the order right when you're saying it. So typically we say the projection of this vector onto this vector. And for the sake of naming this, we're going to let V be a vector that's only there to just indicate direction. Think of it like a unit vector. So the projection of G onto V is essentially if I take that big press that I talked about earlier and I smush the vector onto that line V. Okay, so if I take this and I smush it flat, that gives me the projection of G, right? That's the thing that's being smushed onto V. That's where we're smushing it into. And this would actually give us R1. So R1 is a projection. It's the projection of my gravity vector onto V, which indicates the direction of the ramp. And when we talk about the notation, this is our notation. So projection of G onto V is equal to R1. All right, and then R2, we call the vector component of U that is orthogonal to R1, which makes sense because this R2 is perpendicular to R1. Another neat thing here is that when we decompose this vector using projections, or as we'll see, the dot product in some case, we can actually use that to rewrite this gravity vector g as the sum of those two vectors, so that it's equal to the projection of itself onto v plus the vector that's orthogonal to that. All right, now let's look at an example. So we have that a vector u. All right, so we're given a couple of things here. We have got the vector u is equal to 5, 10 in component form. We want to find the vector component of this that is orthogonal to v. All right, so other information that we're given is that W1 should be arrows. W1 is the projection of u onto v, and it's equal to 8, 6. W2, and also note that u is W1 plus W2. So first thing we note, yeah, first thing we note here is the sum, right? Because that basically gives us everything that we need. So we know that u, which is equal to 5, 10, is equal to W1, that projection, which is 8, 6, plus this vector W2 that has these two components that we need to figure out. And this really is just simple arithmetic, right? Because notice when we add vectors together, we add component-wise. So 8 plus A is the first component. 6 plus B is the second component. So I know that 8 plus A has to be equal to 5. All right, and that would mean that A has to be -3. And I know that 6 plus B has to be equal to 10, which implies that B has to be equal to 4. So W2, that's going to be the vector that is orthogonal to V, right? Because remember, V is going to go in the same direction as W1. All right, so W2 is this vector. And there we go. So I mentioned that we could actually use the dot product to find these projections. And here's that relationship. The projection of u onto v is equal to the dot product of u and v divided by magnitude of v squared. Remember, another way you can figure that one out is v dot v. Whatever that scalar quantity is, because that's a scalar, we multiply by the vector v. Okay. So other thing I want you to note here, if you think back to that example we did earlier, you have to know what kind of quantity your every little step is going to be. We know that this is a scalar. We know that this is a scalar. So overall, all the stuff in parentheses make a scalar. We know that v is a vector. If I take a scalar and I multiply by a vector, the result is a vector. So when we talk about the projection is a vector quantity. All right. So with that in mind, let's look at another example. So let's say that we want to find the projection of u onto v and the vector component of u orthogonal to v. So this one's asking us to do a couple of things. First, let's get our projection. So to get the projection, I need to know my dot product, u dot v. And since we know the component form for both vectors, we can use that formula to find the dot product. First times first, 7 times 3, -5 times 1, and 2 times -2 gives me a dot product of 12. We also need to know norm squared or the magnitude squared of v, which remember, we can also use the dot product v dot v. So if I do that, we get 7 squared plus 1 squared plus -2 squared. So I get 54 for that. So the projection then of the vector u onto v is going to be equal to 12 over 54, which is going to reduce 12 and 54 are both multiples of 6. So it's actually going to reduce to 2 over 9 times the vector v. So we know that the projection is going to be 14 over 9i plus 2 over 9j, oops, 2 over 9j minus 4 over 9k. That is our projection vector. So again, this would be like if I were to draw these vectors in three-dimensional space. Right, we know that u would go 3 in the positive x, 5 in the negative y, and then up 2. So that's going into the page, and that's our vector u. I know that v, we're going to go 7 in the positive direction, 1 in the positive direction, and then down 2. So drawing my little wedge there, we end up with this vector v. So this would be like if I were to take a sheet of paper, slide it so that both of these vectors are on that paper, right? That would define a plane. From there, I would smush the vector u straight down onto the line v. The result would be this little guy that we just computed. That's the projection. So 14 ninths I plus 2 ninths j minus 4 ninths k is this guy. The other thing it told us to do is we want to find the vector component of u that is orthogonal to v. So kind of going back to what we did in that last example, we know that u has these components, and we know that it's going to be equal to this projection vector plus some other vector, a, b, c. Yeah. So essentially I need to figure out what a, b, and c are by just combining these components together. So if I have 14 ninths and I need to add up to 3, what do I need to add? Well, we know that 3 is 27 over 9. So that means that a would need to be 13 over 9. So if I add 14 over 9 plus 13 over 9, I would get 27 over 9, also known as 3. For b, I have 2 ninths. I need -5. So -5, remember, can be written as -45 over 9. So if I have +2 over 9 and I want -45 over 9, then I need to take away 47 over 9. Then for C, I have -4/9, and I need to add up to 2, which is also known as 18/9. So if I have -4 and I need 18, I have to add 22. So I now have the three components for the vector component that's orthogonal to that projection. So we end up getting 13/9, -47/9, 22/9. You also could write as a linear combination 13/9i minus 47/9j plus 22/9k.